Hello, everyone. Today, I'm going to be taking a little bit of time to talk about the Ghc Optimization Pipeline, just from a super high level. Ghc transforms a program through several stages as it optimizes it, and I think it can be helpful to sort of have a big picture view of how that all works, just so that when you actually go and try and get some information about what the compiler is doing with your program, then you actually have some idea about where to start and what you're looking at. So I'm going to start with a super simple program that I've written right here, literally just this module. Now, I have a little bit of code down here for the future, just commented out, but really I'm just going to be starting and focusing on this simple function. And I'm just going to be invoking Ghc directly because in this particular case, I don't really need all of the additional stuff that gets sort of printed out and handled by Cabal and Stack, because I'm just going to be looking at this simple, tiny module. So I'm going to start by running Ghc with the C flag, which says it doesn't matter that I'm not providing a main function, I just want to generate a single object. I'm going to turn on force recomp, which just makes Ghc always recompile the module even if nothing's changed, just because of the fact that I'm going to be rerunning Ghc with different flags to get it to print out different things, and I don't want to have to change the source file every time I do. I'm going to enable the optimizer so that it actually does optimization, and I'm just going to give it this module. And oops, so much for having this prepared. All right, there we go. So we compile this function and we get out a .o and a .hi file. .o is the compiled code. The .hi has some metadata about the sort of types and things like that in the file. I'm not really going to talk about that today. The important thing is I'm actually going to rerun this now with this show passes argument, and this will cause Ghc to print out a whole bunch of stuff about what it's doing when it actually compiles the module. So there's just kind of some stuff up here for loading. I'm going to ignore that, but we can see right away that it runs this series, this compilation pipeline, this series of passes, and it starts by parsing the program. That one's pretty straightforward. It just parses the Haskell code. Then it renames and type checks it. I'm not going to spend very much time talking about the type checker, but the renamer is basically saying just figure out where all the names are bound and make it so that every variable has a unique name. And then we start running through the core-to-core optimization pipeline. So the desugaring pass translates Haskell into core, which I kind of mentioned a little bit last video, but it's sort of a simpler intermediate language. It looks quite a bit like Haskell. We'll see a little bit of it shortly, but it's simpler, and so it's easier for the compiler to work with internally in the optimization pipeline. And then it runs a bunch of passes, starting with the simplifier, the specializer, and so on. I'm going to briefly, very briefly, touch upon what each of these passes does in just a little bit. But basically, that is sort of the bulk of what Ghc is doing, transforming a core program, a program in this intermediate core representation, into hopefully a faster and simpler one. And then eventually, after this long series of optimization steps, then eventually we get to core prep, which says after we've optimized the core program, then we're going to sort of prepare to translate it into STG, which is a little bit lower level. And then we do a little bit of STG to STG, which is the STG optimization pipeline. There's a few minor optimizations that Ghc does on STG, but I think it's mostly usefully just viewed as sort of a step towards generating native code. Then we actually convert that into CMM, which is sort of a portable assembly, and then eventually generate native code. So in order to kind of get a feel for how much changes over this whole optimization pipeline, we can pass particular flags to Ghc to get it to print out the output of particular steps. So I'm going to start with the desugarer, because that's sort of where this all gets started. Now, here's our definition of F down here in the result. And there's also this like TR module thing. This is just kind of auto-generated for every single module, and it's not actually very interesting here. So I'm going to pass this flag, I think it's denotypable binds, and just to kind of suppress that other junk. So we only see exactly what we actually care about, which is this function. So right out of the gate, you can see that there's a lot of information here. Most of it is not particularly relevant to what I'm going to be talking about today. Maybe at some point I can talk about some of this metadata that Ghc is tracking. So I'm actually going to pass another flag to suppress that sort of metadata. And now we can see that it looks quite a bit like the Haskell program that we wrote. We have a definition named F. It has a type signature on it. Its right-hand side is a lambda. It takes an argument. And now we have an application of plus, but you'll note that all function applications in Ghc core are always printed out prefix. There's no infix operations. It has this sort of extra argument here, which I'll get to in a little bit. But for the most part, we just apply it to, this is a type application. We apply it to X, and then we apply it to this application of I hash to 1 hash. This is an unboxed integer, so plus takes an int, and so this is just kind of boxing it up. Now, this boxing here is a little bit superfluous because we're just going to be immediately then unboxing it. Plus is going to be immediately unboxing it. So we would expect that with optimizations enabled, Ghc would be able to transform this program to remove at least some of this superfluous boxing. And in fact, if we replace dump ds with dump simple, this is printing out the simplified core, then you can in fact see that this happens. We sort of have, instead of this use of plus, we've replaced it with this use of plus hash, which is addition on unboxed integers. And so we're no longer boxing it up. And then we only need to unbox the arguments and then box up the result. So this is an improvement over the program that we had before. And you can kind of see this is the idea of the core-to-core optimization pipeline. Hopefully we get these nice improvements. And what's nice about core is that it is totally typed. So at each step of this process, we still end up with everything being type correct. And in fact, there's a flag you can turn on called core lint, which will actually type check it, but that's only really useful if you're implementing something in the compiler and you think it's miscompiling something. So, okay. So after the core-to-core optimization pipeline runs, then we end up with STG. Now, STG looks very similar, but it encodes some more operational details. So for example, every function application is fully saturated, but if we disable optimizations here, then you see we end up with a let in the result. So if I disable optimizations and I just print out the final core, in fact, let's print them out side by side. Print out both the final STG results. So this is with optimizations disabled. Then you can see the core version just kind of looks how we would expect. So the optimizer hasn't run, so it still looks kind of this unoptimized version where we're boxing up an integer and just passing it to plus. It's kind of what we would expect. But in the STG, you'll note that we have this introduction of this let, and there's actually a reason for that, which is that in STG, anytime you have to do some amount of heap allocation, each time you need to allocate a thunk or a closure, then that is always going to be represented by a let binding. And so this is a very useful way to immediately get a feel for, how many closures are being allocated, how many thunks are being allocated, how much heap allocation am I actually doing, because it has this strong invariant at the STG level. So sometimes that can be useful if you're interested in super low-level performance details, but in most cases, it's more useful to look at the core. The other thing is that STG, it sort of has these type definitions here, but it's actually not really typed, and there can be ill-typed STG programs, and those still work out. And I'll mention a little bit later about why that is the case. Anyway, let's re-enable the optimizer and take a look at what happens after the STG level. So after the STG level, we get down to CMM, and CMM is really just sort of portable assembly language. It looks quite a bit like assembly language. STG still looks a lot like Haskell. We had, function definitions and lambdas and things like that, but this doesn't look anything like Haskell. This is very much lower level, and it's actually really remarkable that Ghc can go directly from STG, and there's actually a very nice strategy for going from STG down to CMM. If you're interested, you can read. There's a very actually wonderful paper on STG that sort of introduces it. But the basic idea is that at this point, we're basically at the assembly level. We're operating on registers. We have these basic blocks. We have labels. We have go-tos. Very, very close to assembly language. It's just not sort of specialized to a particular architecture. So then if we do, in fact, say dump the assembly code, then since I'm running this on an x86-64 machine, then I'll get x86-64 assembly code out. Now, looking at the output of CMM and the assembly is, I think, essentially never useful unless you're debugging the compiler. Sometimes it can be interesting to look at, but for the most part, I don't think this is really going to tell you very much about your program. But sometimes it is useful to look at STG, and it's definitely often very useful to look at core. So I want to spend sort of the rest of this video just focusing on, mostly on core itself, talking about kind of what actually happens as a program flows through the optimization pipeline, and just to give you some high-level overview of what's actually going on during the core-to-core optimizer. I'm not going to go into too much detail for each individual pass. I'm just going to describe from a high level what's going on and give a few simple examples. So one way that we can sort of start doing this is we can pass the verbose core-to-core option, and this just prints out basically every single thing that happens in the core-to-core optimization pipeline. There's also individual flags you can pass that sort of dump individual passes, but this is useful because it's just going to print them all, and we can see exactly what's going on. So it starts with the desugarer. Now, the desugarer has basically, if you just print out dump ds, then you'll get this sort of desugar after optimization. It's just a little, it's not really the full optimizer, it's just cleaning things up a little bit so that they look a little bit nicer. So you don't have so much silliness in there. So like, this is figured out that these don't need to be recursive. Minor things like that. So let's just ignore that and let's focus on this sort of cleaned up desugared output. So I mentioned that I, wanted to talk about this argument, but there's some other changes as well that happen when we lower from Haskell down to Ghc core. So in order to sort of show some of those differences, I'm going to let this out and use a slightly more complex definition here, which is actually doing some pattern matching. This is a very silly function. It doesn't do anything particularly useful, but it is a nice illustration because we'll see that this pattern matching here gets changed in some way when we desugar the code. So if we look at what happens after desugaring, and you can see the desugar before optimization looks pretty gnarly, but then it cleans up relatively nicely. So this looks similar to what we wrote. We still have a function taking a maybe int, returning an int, and we have some case analysis here, some case expressions, but there's a few things that have changed. One of them is that, core is simpler, so it doesn't support pattern matching kind of as multiple equations. It always turns pattern matching into explicit case expressions, but there's an additional detail here, which is that here we have some nesting of case expressions, whereas before we just had, one sort of block of pattern matching, and that's because in Ghc core, each case expression always just pattern matches on sort of the outermost data type. So this is doing a pattern match on the maybe part of the maybe int, and then we have another case in here, which is pattern matching on the int part inside. And we also have this pattern match here that's just sort of unboxing the int argument before we're determining whether it's 0 or not. But that's just kind of something that happens at the core level, is you have explicit boxing and unboxing. That's not particularly interesting. But this still doesn't really explain the introduction of these weird fnum int arguments. And the explanation for this is that at the level of Ghc core, there's no type classes. This is actually sort of the most significant difference between Ghc core and source Haskell, is that type classes are completely removed. So how is that possible? How is it possible that Ghc can translate a Haskell program removing type classes? And in order to kind of demonstrate that, I have some code down here. So suppose we just have a really simple type class that we define with just two methods here, m1 and m2. And then we have a simple definition, simple type class instance here that just defines an instance of C on bool. And then we have some function that uses it down here. So let's see what actually happens when this gets desugared. So unfortunately, I don't think there's any way to make Ghc sort of print out the data type that it generates, but it generates a data type, a record type for each type class. And the record type just kind of looks like this. It's just a record type where each element of the record is one of the methods of the class. So internally, Ghc transforms this declaration into this declaration. And so the constructor has kind of a funny name. It's this like m.c:/c. And in fact, these module prefixes, I think, actually just make things a little bit harder to read. So I'm actually going to pass a flag to also suppress the module prefixes as well, just to make this a little bit less noisy. And so we can see that we have this application of this record constructor to two arguments, which are the two methods that we've defined for that type class instance. And this is bound to something called $f cbool. And to be honest, I don't know why it's f. I don't know where the f is, but this just means that this is a type class dictionary argument. And this type class dictionary, it's called a dictionary because it's just a record that maps each of the methods. You can look up each of the methods in it. And then when we actually have some code that uses this, so we have the CA constraint in the type signature, then we receive one of these method dictionaries as an argument. And M1 here is now just, it's an ordinary Haskell record selector, right? We can just apply it to the dictionary, pull out the method, and then apply it to the argument. And so this is actually what happens at the core level. In order to translate type classes, to get rid of them completely, they all just get turned into ordinary term-level Haskell code. And this is actually pretty cool. It means that we can have all the nice things that we have in type classes and don't need to worry about them at all in the optimizer. Now, you might ask, okay, well, but how does GHC know which dictionaries to insert in which places? And that is, in fact, the tricky parts of implementing type classes this way. And that is something that the type checker assists with. So the type checker effectively, as it type checks the program, it keeps track of where it needs to insert those dictionary arguments and things along those lines. And so then when the desugarer runs, it's able to use that information to insert those additional dictionary arguments. And that's why when we have this definition of f, we have just direct references to these f num int instances, which are the type class dictionaries for the num instance on int. And those just get inserted basically due to the constraints that were solved by the type checker. So it's just a small piece of information to keep in mind. So all that will be explicit, and otherwise it's just quite a bit like ordinary Haskell code. So let's just kind of walk through from a super high level, very, very high level, what actually happens as we step through the core-to-core optimization pipeline, just to give you sort of an intuition for how GHC optimizes the program. And sort of the core idea, no pun intended, is that we have this sort of general purpose optimization pass called the simplifier. And the simplifier runs many times. There's, in fact, this phase equals here. This says that we're running the simplifier in the initial phase, which is gentle. And there will be other phases later that we run the simplifier. But each time it's just sort of, its goal is to just kind of clean up the program a little bit. So it does lots of little local transformations. And in fact, it kind of indicates here some of the transformations that it does. I'm not going to go into detail exactly which each one of these things does. Maybe at some point in a future video I can talk about them. But it does things like inlining, applying rewrite rules, ADA expansion, cast swizzling, the case of case transformation. I'm not going to explain exactly what these things are, but they're just these little local transformations that can, hopefully improve the program. And in fact, we can sort of immediately see some improvements that get done. So we have this use of negate and plus, and the simplifier is able to say, okay, this negate is applied to this type class dictionary. This is a known type class dictionary that's just defined at the top level somewhere. So we can effectively inline negate and inline plus, and then we get this specialized, we simplified this, so now we just have a negative unboxed numeric constant instead of a use of negate, and we now have this specialized unboxed plus. And so right away, we've got some nice improvements here. Now, this is a really simple program, so we're not going to see too much additional fancy stuff happen as we walk through this. But I'm going to make it just very, very slightly more complex, so we can see a little bit additional stuff happening. I'm just going to introduce a little list binding here. I'm just going to say it's an infinite list of integers. This is not going to be very exciting, but we'll just say then let's pull out the x plus 1th element of this list. And this will just have a little bit more going on here so that we can actually see the optimizer working. So if we rewrite this now, then after we do the desugaring here, then you'll see that that sort of range syntax gets desugared into enum from, which is just a method of the enum type class that we're just generating a list. And then we're applying bang bang to it. Again, everything is prefix, not infix. But now when the simplifier runs, we immediately see that stuff starts happening. Interesting stuff starts happening. In fact, we end up inlining enum from. This gets turned into a use of build, which is constructing a list. And we're given this lambda argument. This kind of has to do with list fusion. I'm not going to go into the details of why this is the expansion here, but you can see that stuff is happening. We're constructing this list here using this other function from some module or some module somewhere in base, and then we are applying it to this argument. Now, there's one thing that I didn't mention here about core, which is that sometimes case expressions can have an identifier in between the of and the open brace with the cases, and that seems very strange. But the reason for that is that this is actually just an alias for this. But this is used everywhere in the body, and it sort of represents the forced version of this. So anywhere that this is used, we know that it's already been reduced to weak head normal form. It's already been forced to be evaluated because we did pattern matching on it. And the optimizer maintains this invariant through the optimization pipeline in order to allow some nice things to happen. All right, so hopefully that all makes sense. So what happens next? Well, so the specializer runs. Now, there's not actually enough going on here to actually see what the specializer is doing, and I'm not going to show an example. If I showed an example of every single one of these, this video would be very long. But basically what's happening here is the specializer would just, if you had some type class overloaded function, then it might generate specialized copies of it that are monomorphic to allow those to then be optimized more aggressively. This is very useful if you're writing very type class polymorphic code. So then we have this levels added pass, which is really just an analysis that keeps track of sort of how deeply nested things are and things like that. And that is then used by this float out pass. And the float out pass, this is one of these reasons that I added this list definition here, is that if you look at this list definition, we have this local list definition, but its right-hand side is totally constant. It doesn't use x anywhere, right? It doesn't depend anywhere on the argument to the function. And so in theory, GHC could lift out this x's definition to the top level so that it would only be evaluated once at the very top of the program, and then it would be shared between multiple applications of f. And in fact, GHC will figure that out. So we can see that now in the body of f, we've got this application of bang bang here to this new variable that's been introduced named LVL_SRI. And you can see that right here. It's this application of build, which then is applied to this lambda, and then this was introduced and is used somewhere as well, or maybe it's used, I don't actually know where this is used. Here, it's used here. So all of these sort of constants have been lifted out to the top level. This is known as the full laziness transformation. And, in some situations, this isn't always a win because it means that this list that we're building here is now a global and it will never be garbage collected. So if we were to, allocate really, really long lists, then this might not actually be beneficial. But in most cases, you're not just going to allocate like a really long constant list. This doesn't happen very often. So in general, this is usually a good thing. And it doesn't just have to be lifting things all the way out to the top level. It can also lift things out of lambdas, but still into sort of local definitions. And so this allows the program to get more sharing when it actually runs, which is quite nice. So then we run the simplifier again, and now we're running it in phase 2, the main phase of the simplifier. And if you're familiar with rewrite rules, the way that rewrite rules work is there's a series of rule rewriting phases, starting with 2, then 1, then 0. That's by default. You can change this, but I think nobody really does. If you're interested in really understanding all the details of what the rewriting passes do and how to write things to take advantage of that, there's a bunch of information in the Ghc User's Guide that is very, very helpful. I'm not going to go into that in any detail right here, but you can see that we're starting with phase 2. We're now doing the case-of-case transformation. We didn't do that because sometimes it can kind of prevent specialization or floating out from working. But now we're going to do that. And so we're doing kind of the full specialization pass. We're going to continue, hopefully doing some things. And I think this program is a little bit too simple to really see terribly much happen. But we will eventually see that indeed in phase 1 of the simplifier, the build function inlines. And now we have a little recursive definition here that just uses cons. This has to do with list fusion again. It's sort of annotated in a particular way, so it doesn't inline until phase 1, but now it actually has inlined. And now we have sort of a nice recursive function that's directly using cons. And for the most part, nothing else really gets cleaned up in any way. This pretty much stays the same. So at this point, we now do float inwards. And float inwards, again, I don't really think we're going to see anything here, but it's basically saying if we have a definition that is used inside of a lambda, and it's really cheap, or we know that the lambda will only be called once, then we can push the let binding inside of the lambda so it's only evaluated when the function's actually called. We don't have to allocate a thunk. This can sometimes also reveal nicer further optimizations. If you're interested in sort of any of these optimizations that I'm not going to provide explicit examples for in this video, you can look up this information on the Ghc User's Guide, and there's just like a bunch of, or not in the Ghc User's Guide, in the Ghc Wiki on GitLab, and there's lots of information about pretty much every single one of these optimization passes. There's also some papers that go into detail as well. I'm just going to try and give a high-level sketch. So then we also have called arity analysis. Now, in order to sort of see what's going on with some of these passes, I'm going to stop passing the suppress ID info flag. Also, I'm realizing it's gotten quite dark since I started recording this, and so now it looks like I'm kind of sitting in the dark here. That's okay. So if we scroll back up a little bit, this now re-enables printing all this metadata next to each identifier. And there's actually a lot of interesting metadata that Ghc tracks as things propagate through the compiler. So again, I'm not going to go into all the details about what all these things are. That would take much too long. But we can see that this called arity analysis pass is going to, before we have this go function here that was generated after we inline build, and it has arity 1, which is to say it has a single argument. Now you might say, like, this is a little bit silly. We can just determine that it has arity 1 by looking at the right-hand side, which is true. But sometimes the arity actually doesn't match up with, like, for example, this might be a curried function where there's like a let in between. Like we might have a lambda and then we have a let and then return another lambda. And so just by looking at the type, it wouldn't actually tell us that there's sort of the sort of native arity before we do some actual computation. So that's what this specifies. But now we also have something after called arity analysis, which is this call arity here, which says that when this is called, it's always passed one argument. Now, you might say, okay, well, this is not very interesting because the call arity is exactly the same as the arity, but in general, that might not be the case. And if that weren't the case, then if they were different somehow, then Ghc might be able to use that information to eta expand or eta reduce the definition in some way. So this is sort of an analysis pass that is then used by later passes. And this is a very common theme in the Ghc optimizer. It's sort of this modular approach where you have passes that are sort of specialized into specific things like adding levels, floating things out, and then we can run the simplifier to kind of take advantage of some of the information that we've learned. So now that we've done this called arity analysis, we're going to run the simplifier again, and this is running in the final phase post call arity. And I think presumably this eta expansion is going to be driven by some of that call arity information, although I don't know for sure. I'm not an expert on every single phase of the Ghc optimization pipeline. So then after we do that, then we do demand analysis. And demand analysis is quite interesting. It's a combination of strictness analysis and use analysis. So it determines whether or not arguments to functions are used and whether or not they're used strictly. So each one of these functions gets this stir equals. This is a strictness signature. Which, you know, I'm actually a little bit confused about the strictness signature because my understanding, if I'm reading it correctly, is that this says that the argument is used exactly once and it's used lazily. But it doesn't really make sense to me because it's used strictly. So maybe I'm misreading these. The syntax for these strictness signatures changes. It's changed a few times when I've been reading this. But there's, again, a page on the GitLab, the Ghc GitLab, that goes into the detail about all the strictness signatures, and they can be kind of complex sometimes. Like this is saying that this is a product type that has a single argument, and then that, or a single bit of single field, I guess, of contents. That's this sort of boxed integer. We're saying that that boxed integer is used exactly once as well. And so this information is used to drive various other optimizations. The most significant one are, I guess, constructor product result, although maybe it doesn't use, but the worker wrapper transformation definitely uses this. And again, I'm not going to go into the detail about what exactly CPR and worker wrapper are. I think the worker wrapper transformation is really cool. I would like to do a video about that in the future, but basically this is just doing and annotating these things with information that can then be used by future optimization passes. Constructed product result, actually we will be able to see something happening here, which is kind of cool. Constructed product result analyzes functions, determines whether or not they return product types that are directly constructed in sort of tail position in the function. So in this particular case, we can see that here we have this go function that's building up this list, and it returns an application of the cons constructor. Now, in this particular case, this isn't super interesting because CPR only sort of works one level deep. So the rest of the list is still just an opaque list. But if this were, say, a tuple, a pair of two things, then this would be much more useful, because what this ends up doing when we run the worker wrapper transformation is you'll see that we end up rewriting this function into a version of the function that returns an unboxed tuple instead of a list. So if this were, originally a tuple of like, int and a bool, then we would unbox the tuple in return position. So we wouldn't even allocate a tuple at all in, situations where we can then just use the unboxed tuple directly. In this case, it's a little bit less useful because we still have to allocate the list for the second argument here. But it sort of illustrates the general ideas that this allows us to unbox multiple results returned from the function. So that's pretty cool. The worker wrapper transformation, as I sort of alluded to before, also does a bunch of other things like unboxing, propagating strictness information. I think it would be really cool to do a whole video on that in the future. But for now, again, it's just kind of consuming the information from these previous two passes, demand analysis and CPR, to do some nice things to our program. All right, so let me run the simplifier again, post worker wrapper, now that we've generated these workers and wrappers, and hopefully some things will simplify out. And indeed, we can see that this looks a little bit simpler than before. I'm not going to go into the details. You can run this yourself and inspect it if you want. And then we do exitification. And to be honest, I have absolutely no idea what exitification does. I think it has something to do with like loops and tailed recursion and join points. I don't know, maybe I'm totally wrong. Every once in a while I see it. It doesn't normally have that much of an impact on stuff that I'm looking at, so I've never really bothered to figure out exactly what it's doing. But if you're interested, again, you can look up. I'm sure there's some easily accessible information. Ghc is amazingly well documented, just in terms of like internal docs. So then we're going to do levels added again and do another float out, because now we've rearranged a bunch of things, and so maybe we can float some more things out. And then finally, we're going to do common sub-expression elimination. This is very common. Essentially, every optimizing compiler does some form of CSE, common sub-expression elimination, which I don't think is really doing a whole lot here, but it basically just means if you have expressions that are the same expression and used in different locations, then you can introduce a let binding, pull them out, only compute it once, and then just use it twice. And that's particularly nice in Haskell, because in Haskell, you know, Haskell's pure, so we don't have to worry about sort of removing side effects and things like that. So we can do CSE very, very generally. Then finally, we do another float inwards pass, one final phase of the simplifier, final phase, just to do a tiny little bit of additional cleanup. And then we do one last pass of demand analysis. Now, we're not actually going to use this demand analysis when optimizing this module, but it might be useful, because we need to make sure that the demand analysis that or the demand information, the strictness signatures that we put in the interface file, which says what like strictness signatures and things like that are for definitions defined in this module, then when we are compiling other modules, then they can make use of that demand information. So we want to make sure that all the demand information is correct now that we've finished kind of rearranging things. And at this point, we're sort of done from the perspective of what goes into the interface file. So the rest of this is now just going to be for code gen. So we're going to run the tidycore pass, which, to be honest, I don't really know what the tidycore pass does. It does some simple cleaning up. I don't know exactly what that means. I always see it and think, I wonder what exactly is going on. But core prep is specifically saying, well, okay, we're going to rewrite things in preparation to generate STG. So we're going to rearrange like cases and lets so that they are sort of in the same structure that they are in cases and lets. And then we're done. We're done with the core-to-core optimization pipeline. We can run STG to STG, code gen, and so on. So what actually goes on in STG to STG? I might have mentioned it before. There's like, well, okay, one thing that I wanted to mention is that I said STG is untyped, and one reason is that STG to STG does do an additional common sub-expression elimination pass, because if you have two expressions that are different types, but are actually the same expression, then STG to STG, they can be commoned up by a CSE pass in the STG optimizer, because STG is untyped. So that's like one example of an optimization that happens there, but for the most part, they're very, very simple. And then there's sort of a standard set of optimizations that are done when optimizing the assembly code, you know, register allocation, control flow analysis, simple stuff like that, and then we generate assembly. So that's about it. So that's really all I kind of want to talk about for now. Obviously, there's lots and lots of stuff in here that's super cool that I've glossed over. And if you're interested in any particular aspect of it, or you have some question, then please leave a comment, and at some point maybe I will make a subsequent video that goes into more detail about specific aspects of the optimization pipeline. But for now, I think this is reasonable, and hopefully you find it helpful. If you're interested in kind of understanding how your Haskell program gets optimized, then maybe one of these passes is more relevant for you than the others, and there's information in the Ghc Users Guides about all the flags that you can pass to print out specific things. In fact, there's even more information you can print out than what I've printed out here. So definitely give that a look, and I'll see you next time.